focusing ourselves to this type of, again, for today, we're going to be focusing on this type of force. Again, this is one of the common forces that you'll be dealing with. So this is friction. So we define what friction is and its direction, but mainly we'll be talking more about this force. And actually, you can get the magnitude of the friction force. So friction is a force that always opposes. So it will always oppose the motion of an object. And X, so X parallel to the surface in contact. So just to remember that it's always parallel to the surface in contact and opposite motion. The magnitude F of F is given by the friction in general. FF is given by mu times the normal force. So as mu gets larger, F of F increases. So if you can see here, the figure at the right, the object is acted upon by several forces, but there should be, if you're going to draw the free body diagram of this object, normal force is upward. So this is your Fn. And then we know that this is acted upon by gravity, so Fg. Okay. So again, in our case, to get Fg, we just use the formula m times g. So, and then we have the frictional force. Applied force will make this object move to the right. So this is my Fa. And the frictional force must be in the opposite direction. So that's your Ff. So for this particular object, you have four forces acting on this. Although in our previous discussion, we tried to assume that friction is non-existent. So that's why we can eliminate that one. We can eliminate the friction force. But if in reality, friction is present. So friction, so this is according to experiments. And by the way, this is an empirical formula. F of F is equal to mu times Fn. That is coming from as a result of experiment. So friction depends on two things. The force pushing two surfaces together. So it is just how large the two surfaces in contact are pushing each other. And remember that the normal force is just the reaction force by the surface. So therefore, that's one of the quantity involved there, Fn. And then the nature of two surfaces in contact. Okay. So the mu, that is given by the value of mu. Mu is dependent on the surfaces in contact. So example, you have glass on wood or rubber on glass, or you can have wood on wood, could be different also. You can have a metal on ice, okay? Even metal on ice still have certain amount of friction there, although that is relatively small compared to if you have maybe rubber on a glass surface, okay? So it does not depend on So it does not depend on the area of contact of contact. So that means that if you're gonna orient, as long as the weight of the object does not change, because essentially the weight of the object is its way of pushing the surface down. In a way, the surface will react even with normal force. So if you're gonna orient your object differently, well, the weight essentially there doesn't really change. So the area of contact is, does not affect friction, okay? And speed. So no matter how fast it's moving, well, friction will still be the same. So essentially, this is based on experiments. Essentially, it's only dependent on the type of surfaces in contact as well as the normal force. Again, the normal force gives you the idea how hard these two surfaces in contact push each other. So again, their direction of forces would be in different directions, but their magnitudes would be the same. So let's take this example here. So a 5 kilogram block is sliding across a horizontal table with a coefficient of friction of 0.25. What is the value of force of friction? So you're given by the following here, coefficient of friction. So if you can see, coefficient of friction is unitless. So it doesn't contain any unit. It's just a number. And you have the mass of 5 kilograms. So what is the volume of the force of friction? So value, so it's just asking for the magnitude. So remember that the magnitude is given by this formula here. So let's see. But before we start our solution, you always start with your free body diagram. So I'm gonna start with free body diagram. So I'm talking about this object on a table. So this would be my object. Again, you just represent it with a dot, that's fine. And then just place the forces acting on the object. Well, we have here Fg. Again, the magnitude of your weight is just given by mg. And you have the normal force. Okay. And that is given by Fn. So remember that, let's say, sliding across, well, it doesn't specify if it's to the right or to the left, but it doesn't matter. Well, let's just say that its velocity is going into the right direction. So this is my positive direction, and this object is moving to the right. So friction must be, remember that the surface is along this. So this is your surface here. So if this is your surface, so how would you identify the friction force? Well, the movement is to the right, and we know that friction force is parallel to the surface, but opposite in direction of motion. So I will draw my friction force to the left. So friction force must be to the left. Okay. So these are all of my forces. There are three forces acting on the object. Remember that there's no pushing force, or there's no applied force in this case. So maybe perhaps this is now by the time that some applied force is already, it's just the same thing as pushing an object. If you're going to push an object, eventually it will leave your hand. And once it leaves your hand, it will slow down until it stops. The reason for that is, well, you have friction. And if you can see, my motion is to the right, but since there's a force going to the left, this will make my object move slower and slower and slower. And partly, I think you've done this one in your experiment, in the previous experiment. So once the applied force is gone, you observe that the only force acting in the direction of motion of the object is friction. So we can assume that Fn and Fd should be equal, okay? So if we're gonna write the things that we know, so the given, we have the mass of 5.00 kilogram, and then mu, so that's my coefficient of friction. Again, coefficient of friction is just the value of your mu. And it doesn't contain any unit. Okay, so it's just a number. So it's mu. And what else? Well, G is already, you know that that's 9.80 meters per second squared. So from now on, just use that value in computation for the weight. Okay, and then we want to know the magnitude of the friction. Okay, so the value. So in our solution, so we always start with the equation that we want to use. So we're talking about friction force. So that means that I'm going to use the expression for the friction. It's given by mu and then Fn times the normal force. So if you can see, mu is given. It's directly given in the question. But how about the normal force? Well, if you can see the normal force, there's no vertical motion in this case. So if there's no vertical motion, and since there are only two forces on the y, in the vertical component, again, the vertical forces, I can say that Fn, the magnitude of my normal force, is just equivalent to the magnitude of my weight. Again, that is from the first Newton's law. I'm just going to specify that one here. First law, that Fg or Fn plus the negative of Fg is equal to 0. First Newton's law, net force is equal to 0. So from there, you can actually see that Fn is just equivalent to Fg, which is mg. So even though indirectly it was not given indirectly in this particular question, we can solve for Fn. Fn in this particular case is just equivalent to mg. But we have done this in the previous question, that this is only true if the object is lying horizontally on the surface and there's no other applied force. That means that you are not pushing it downward or somehow applying force upward. So this is only true in this case if, again, lying horizontally, because if this is somehow angled off, remember that Fn is no longer equivalent to the weight. Okay, so again, this is only true in this particular case. It's lying flat horizontally on the surface, as well as there's no additional force being exerted on my box, downward or upward. Because remember, if I just push it downward, if there's an additional force downward, that would affect the value of your normal force. Okay, so hopefully you can remember that. So I'm just going to substitute everything. So that would be 0.25 times the normal force of mg, but my mass is 5 times 9.8. So frictional force, the magnitude would be around 12 newtons. Okay. So the value of friction, well, again, it's asking for the magnitude, so I don't have to write the direction. So my answer is 12 newtons. So the value of the friction is 12 newtons, and its direction is to the left. Again, it depends on where the object is moving. If you said that the object is sliding to the left, you should indicate that the direction of friction would be to the right. Okay, so just be careful with that. So let's move on to example number 2. A force of 14 newtons is needed to keep a 14 newton block moving at a constant velocity. So these terms, you should be careful with these terms here. Remember, the object, 14 newtons. So that means that you're given the weight, not the mass. Okay, this is common mistake by students. Even though they're already given by the weight of the object, you will still be using 40 times 9.8. Well, it's no longer weight. Okay, so this is already the weight of the object, and it's moving at a constant velocity. What is the coefficient of friction between the block and the surface? So you're solving for the coefficient of friction. So between the block and the surface. So again, always start with a free body diagram. Free body diagram. In this particular case, you're talking about the object. So I just going to represent that one by a dot. Well, you have here 14 newtons. So what is that 14 newtons? That would be interpreted, if you can see, that would be your applied force. And let's say, for example, I'm pushing to the right. So it doesn't specify there, but then again, doesn't matter. So this is my FA, and this is 40 newtons. And then again, always you have the FG, the weight of the object, and this time, this is 40 newtons, okay? And I know that I have a normal force because this is in contact with the surface, so I have a normal force there. And if this is moving to the right, well, obviously usually the direction of the applied force would be the direction of motion of the object. So the object will tend to move in that direction. So I have friction. Okay. Friction to the left. Okay. And we have here that it's moving with a constant velocity. So what does it mean? That means that the net force is equal to 0. So it also means that both the x, net force along x, and the net force along y is also equal to 0. So if that is 0, by just looking at your free body diagram, you can say that this applied force must be equivalent to the frictional force, as well as your normal force is equivalent to the Fg. Okay? So again, how do I know that one? Well, the object is moving with a constant velocity. And according to first Newton's law, the acceleration is 0 there, so the net force is equal to 0. So in my solution, so again, for my given quantities, you have Fa is equal to 14 newtons, Fg is equal to 40 dot newton, and you're solving for mu, okay? So for my solution here, well, by just looking at the free body diagram, Fn is just equivalent to Fg, which is equivalent to 40 dot newtons, okay? So I can see, again, the vertical component of the vertical forces, the sum would be equivalent to 0, but there are only two forces directed on different directions. So it must be that the normal force must be equivalent to your Fg, as well as you can say that Fa would be equivalent to your Ff, which is equivalent to 14 newtons, okay? So again, I can say that they are equal because of the fact that the net force along X is 0, as well as the net force along Y is 0. And again, how do I know that one? From the problem, it's given that it's moving with a constant velocity. So Fa is also equivalent to 14 newtons. Now, our starting equation would be, again, we're talking about friction. So the ideal formula that we'll be using is the expression for friction. And then you move from there. We're solving for mu. So that's mu Ff over Fn. And just try to check whether all of these quantities are given. Well, if you can see, Fn is given by 14 newtons, so that's given. We also have Fa, or equivalent to Ff, so that's 14 newtons. So I'm just going to substitute these values. So Ff is 14 newtons divided by 40 newtons. So if you can see here, you can also verify that your coefficient of friction is unitless, because the units are just cancelled in this case. Newton over Newton is just 1. So you get the value of mu, which is 14 divided by 40, that's 0.35. Okay, so that should be the coefficient of friction. Okay, let's take example number 3. So Marlo and Laggy are sliding a 3 times 10 to the power of 2 kilogram safe across the floor to their getaway car. The safe slides with a constant speed. If Marlo pushes from behind with a force of 3 times 10 to the power of times 10 to the power of 2 Newton, and Laggy pulls with a rope from in front with a force of 3.9 times 10 to the power of 2. what is the coefficient of friction? So it's going to take note of, so you're given here forces of the unit Newton. What is the coefficient of friction between the safe and the floor? So we're looking at the coefficient of friction again. So again, before starting your solution, start first with the free body diagram, always. So again, I'm gonna indicate, you can use a box or a dot to represent the object. And then from there, you indicate the different forces. So if this is my safe, well, it's sliding horizontally in the floor. So this would be my FG, that is downward. Remember that again, this is just mg. So in this particular case, if you can see, this is mass because of the unit kilogram. And then I have a normal force. And then what else? Let's say, for example, again, this is moving to the right. So that must be the direction of the applied force. In this case, there are two applied forces. Done by Marlowe, which has the magnitude of 3 times 10 to the power of 2, and one is by Laggy, which is 3.9 times 10 to the power of 2. So if I'm going to draw that one out, that would be, again, if this object is moving to the right, so this would be the force exerted by Marlowe, which is equal to 3.00 times 10 to the power of 2 newtons. And you have the force exerted by Laggy. So remember, from the behind and then pulling it, so therefore these two forces are in the same direction, okay? So one is pulling it, one is pushing from behind. So essentially, if you're going to draw that one in your free body diagram, their direction would just be in the same direction. So it should also be to the right. So this is force exerted by Laggy, which is 3.90 times 10 to the power of 2 newtons. And lastly, you have the frictional force. So that should be in the opposite direction of your motion. Again, if the object is moving to the right, so movement in the same direction as your applied forces. So FF would be in the opposite direction, but parallel to the surface. So this is my FF. And for your solution, you have to indicate the information that A is equal to 0, because it's moving with a constant speed. So that means that net force along X is 0, and the net force along Y is also 0. Okay? So one is obvious here. Fn has the same magnitude with your Fg. So Fn is just equivalent to Fg, which is equivalent to mg. So you can get Fn is equal to 3 times 10 to the power of 2 times 9.8. So Fn, again, in this particular case, we can say that Fn is equivalent to the mass times the acceleration due to gravity. So this will give me an answer of 2.94 times 10 to the power of 3 newtons. So this is now the weight of the object. So this is also the weight of the object. That because of their, if you can see in the free body diagram, there should be equal.
Wait, Mr.
Okay.
Fellerin?
Yes.
Sorry to interrupt, but is Fg equal to the weight of the object always?
Yes. Fg, we use Fg to denote the weight of the object. Yes,
Okay, okay. Thank you.
you're welcome. So, uh, in this case, again, I can say that the normal force is equivalent to the weight of the object. And since the weight of the object can be determined by the product of the mass and the acceleration due to gravity. So don't take this one as the normal force as always equal to the mass times acceleration due to gravity. Again, we can only do that here because of the fact that the normal force is equivalent to your weight of the object. So it's not automatic. Again, we've shown that one in our previous uh, example or discussion in the previous lessons, that somehow if the object is lying at an inclined, the normal force is not essentially equivalent to the weight of the object. So somehow there would be some changes, as well as even though the object is lying horizontally, but there's an applied force downward or upward, the normal force will change. So we're solving for mu. Mu is equal to F over Fn. So we're given the normal force, but we need Ff to solve for the value of mu. But based on the drawing, if you can see, that would be the friction force is lying on the horizontal axis. So you're talking about the horizontal forces. So you need to solve Ff. Again, we can use the fact that the net force along x is 0. But what are those forces? So if you can see, what are these forces here? That is made up your FF, FM, and FL. So that means that, say, for FM and FL, if I use the right as positive, so that would be FM plus FL plus the negative of FF is equal to 0. That means that the algebraic sum of all of the horizontal forces should be equivalent to 0. So there are three forces, two forces to the right and one force to the left. However, I'm solving for FF and solving this algebraically. FF is just equivalent to the sum of FM plus Fn. No, not Fn, but FL. Sorry. That should be FL, force by length. So, and we can also see that one here, that this particular line, the sum of this, should be equivalent to the sum to the left. So these two should be equal also, the length. But the length to the right should be the sum of Fm and Fl. The sum of those will give you the frictional force, or the magnitude of the friction force. So they should, excuse me, 390 FF, so 690 newtons is your FF. So I can substitute that one in your FF. So that should give me 3. Mu is 0.235. So, okay, can we have a 10-minute break? Yeah, it's